So hi guys, we are back with another video that is we're gonna discuss the uh, calorimetry part. So I think we discussed the tutorial of the calorimeter once, right? Like the tutorial session 1 is already posted. So if you have not yet covered that, you will have to first of all cover the tutorial session 1 in calorimetry, and then thereafter you will have to watch the current tutorial session 2, right? So I think we covered up to the 9th question. So let us go from the 10th question onwards. All right. So yes, so this is regarding, simply it says a vehicle of mass 1280 kilograms. Okay, a vehicle of mass 1280 kilograms moving with a speed 108 kilometers per hour comes to rest by applying brake, right? So then they are saying a brake pad is 8 kilograms and it is made out of a material of specific heat capacity of this much. Find the temperature rise. You need to find the temperature rise of a brake pad if 50% of the kinetic energy of the vehicle is converted into, if 50% of kinetic energy of a vehicle is converted to heat in the process, and brake pads in all four wheels contribute identically to stop the vehicle, right? So pause the video once and then once again go through the question well, try to understand the question well, absorb all the data, and then let's go for the discussion, right? Okay, so let us draw a diagram simply, right? So right, so yeah, this is the 10th question, right? So in the 10th question they're saying there is a vehicle, right, which has four wheels, right? So the mass of the vehicle is 1280 kilograms. Mass of a wheel is, sorry, brake pad, mass of a brake pad in the wheel is 8 kilograms. So initially this is moving with what velocity? It's moving with an initial velocity of 108 kilometers per hour, and then finally it comes to rest. It comes to rest. How exactly is it going to come to rest? By applying the brake, right? So while this was moving with this velocity, suddenly at maybe at the point A it applies the brake, and then at the point B it comes to rest, right? Okay, so now then they are saying 50% of this, like actually what has happened, initially it had a kinetic energy, and when it stops, its kinetic energy is going to become zero, which means its kinetic energy has lost, right? The total kinetic energy has lost. So they're saying 50% of this kinetic energy, 50% of this kinetic energy was lost to like the 50% of the kinetic energy of the vehicle is converted to heat. They're saying 50% of the kinetic energy of the vehicle is converted to heat, right? So let us find that 50% of the kinetic energy, right? Let us find the kinetic energy loss. Kinetic energy loss. First of all, let's find the kinetic energy loss. Half m u squared minus half m v squared, right? Half, what is the mass? 1280, the mass of the vehicle. Initial speed 108, right? So in 108, if you divide by so 108 in meters per second is going to be 30 meters per second. And if you convert 180 kilometers per hour into meters per second, it's going to be 30 square. Finally, it comes to zero speed, which means its final kinetic energy is zero. So the kinetic energy loss is 1280 divided by 2 into 900, right? So something around 576,000 joules, right? So they're saying 50% of this kinetic energy, 50% of this kinetic energy was converted to heat. So let us find the 50%. Actually, 50% of it means exactly this. So divided by 2, right? It's going to be 288,000 joules, right? 288,000 joules. This was converted into heat. So how do we equate it? Kinetic energy loss equals to heat energy gained by brake pad. How many brake pads were there? 4 brake pads were there. So this should be multiplied by 4, right? Heat energy gained by one brake pad into 4. Actually, all 4 brake pads absorbed this kinetic energy loss, right? So 288,000 joules is equal to M. What is the mass of a brake pad? MC theta. Mass of a brake pad is 8 kilogram. M. The specific heat capacity of a brake pad is 600 joules per kilogram. So this is the increasing temperature, it says you rising temperature delta T into 4. So if you simplify this, you're going to get delta T to be 15 degree Celsius. If you simplify this, you're going to get the answer to be as 15 degree Celsius, right? So it's not a very difficult question, right? Simply the kinetic energy lost was absorbed by the brake pads to increase the temperature of the brake pads. There was actually 4 brake pads in 4 wheels. All the 4 wheels combinedly absorbed this kinetic energy lost. Actually, 50% of this kinetic energy lost, right? Right. So let's see the 11th question, guys. So it says, find the final temperature of the mixture if 25 kilograms of water, which is at 100 degrees Celsius, is mixed with 15 kilograms of water, which is at 20 degrees Celsius. Right? So it's a pretty easy question if you see, right? It's like they're saying, yeah, they are saying, right? So yes, they are saying there are 2 water vessels separately. One is of mass 25 kilograms and another is of mass 15 kilograms. This is in temperature 100 degrees Celsius. This is in temperature 20 degrees Celsius, right? So both these water are put into one vessel, right? So what will be this vessel is going to be of temperature, like after both are mixed together, it's going to reach a common temperature, right? Theta, like an equilibrium temperature, theta M. Let us assume theta M is going to reach a equilibrium temperature, right? So actually, so we need to find this equilibrium temperature. Like simply, this is the mixture. What they're asking is the temperature of the mixture, right? So now, who is going to supply heat? This guy, right? This water vessel, the water column in this vessel is going to supply heat to whom? To this guy. This guy is going to absorb the heat supplied by this water column, right? So simply, if we assume this as A and this as B, right? So we can write the equation as heat supplied by A equals to heat gained by B. So heat supplied by A, MA, CA, delta theta A. So heat gained by B, MB, CB, delta theta P. What is the mass of MA? MA is 25 kilograms. What is the mass of, what is the, this thing? So it's C. Simply, let's assume the calorimeter. I mean, like, simply the specific heat capacity is C. Specific heat capacity of water is C, right? So the change in temperature is what? Initially, it was at 100 degrees Celsius. finally it's going to decrease its temperature to from 100 degree to this much, right? So let us assume theta m. What is the mass of B? 15 kilograms. What is its specific heat capacity is also C, right? So the same, both are water, right? What is its change of temperature? So it was initially at 20 degrees Celsius. It's by absorbing heat, it's going to increase its temperature to theta m. So what is the temperature difference? Theta m minus 20, right? Theta m minus 20. So if you simplify this, right? So these two, this cancels somehow. If you simplify, theta m is going to be 70 degree Celsius, right? So that's a pretty easy question, right? So yes.
So the 12th one, let's discuss the 12th one. So they're saying there is 0.08 kilogram of water in a calorimeter of mass 0.15 kilogram, and the specific heat capacity of the calorimeter, they have given it to be as 800, and initially both the water and the calorimeter is in 16 degrees Celsius, right? And then they're saying an iron ring of mass 0.1 kilogram, which is heated to 100 degrees Celsius, is put into the calorimeter, right? And then they're asking to find the final temperature of the calorimeter. They have given the specific heat capacity of the ring as well, right? Ring and the water. So initially, let us draw a figure for this, right? So the 14th question, right? The 12th one. So in the 12th one, we see there's water. How much? 0.08 kilograms, right? And then what is it? What else is there? The calorimeter is of mass 0.15 kilograms, right? And then the specific heat capacity of the calorimeter specific heat capacity is 800 kilograms per kilograms joules per degree Celsius, right? And then initially this was in what temperature? Theta 1. It was in 16 degrees Celsius, right? So to this they are inserting a ring which was of mass 0.1 kilogram, and which was of temperature 100 degrees Celsius, right? Which was at 100 degree Celsius was put into this, right? What happens as a result? As a result, what happens is now the heat given by the ring, heat is going to be given by the ring, and heat is going to be absorbed by the calorimeter and the water, right? So these guys are going to absorb the heat. So, and then finally all these three, the ring, the water column and the calorimeter, is going to reach an equilibrium temperature, right? So that is what we need to find, right? So yes, here simply what is it? Heat given by the ring equals to what? Heat absorbed by who? Heat absorbed by water plus calorimeter, right? Heat absorbed by water plus calorimeter. Heat given by the ring is what? What is the mass of the ring? If you see the mass of the ring is 0.1 kg. It was initially at 100 degrees Celsius, and then after releasing heat, it reached theta 2 temperature, right? So therefore, its mass is 0.1 kilogram. If you see its the specific heat capacity of the ring, they have given it to be as 400, right? 400. Its temperature decreased from 100 to theta 2. So heat given by the ring is equal to heat absorbed by water. So what is the mass of water? 0.08 kilograms. What is its heat capacity? 4200. What is its temperature rise? Actually, it raised its temperature from theta 1 to theta 2, isn't it? So from theta 1 to its temperature rised to theta 2 due to the absorption of heat. So the calorimeter is also the same. The calorimeter also was initially at 16 degrees Celsius. It also, by absorbing heat, it reached theta 2, which means both these guys are going to, the temperature difference between them is going to be theta 2 minus 16. So the calorimeter, if you see the mass of the calorimeter is given to be as 0.15, and the specific heat capacity of the calorimeter is given to be as 800, right? So if you see the temperature difference of both these guys, they were initially at 15 degrees Celsius, right? Sorry, 16. Finally, they reach a theta 2 from 15. So therefore, the temperature difference is this much. So if you simplify this, you are going to get theta 2 to be as 28.8 degree Celsius, right? So I guess the question is not that difficult. All right. So yes. So it says a calorimeter contains, sorry, let's go for the 15th question, guys, right? So let us go for the 15th question. Right. So the 15th one. All right. It says, so this is the 1982 A-level problem, right? So 1982 essay question. So I think there's going to be plenty of simplifications, but let us not worry about the simplifications and all, right? So let's focus on the concept. All right. So okay. So they are saying define the specific heat capacity. Yes, you can do that, right? Let's consider only the question here. A copper sphere is heated to 72 degrees Celsius. Okay, a copper sphere, right? And it is put into a container of water at 24 degrees Celsius. It is put into a container of water which is 24 degrees Celsius. This container is well lagged, which means no heat loss from the container. The container and its content come to a steady temperature of 40 to 48 degrees Celsius. The container and its content, like content means now inside the container there's water as well as the copper sphere, right? So they come to a steady temperature of 48 degrees Celsius. Now the copper sphere is removed, and water and the container are allowed to cool down to the room temperature. Then a steel sphere heated to 48 degrees Celsius is put into the container, right? It's a steel sphere which is heated to 84 degrees Celsius is put into the container. Then the new equilibrium temperature was 54 degrees Celsius. Then the steel sphere was also removed and the container is cooled down to room temperature. Finally, the copper sphere and the steel sphere, both heated to 72 and 84, are put into the container. Determine the final temperature of the mixture. So in this question, they have not given, if you see, the steel sphere's specific heat capacity is not given, copper sphere's specific heat capacity not given, water's specific heat capacity not given, right? So in that case, we will have to maybe find the specific heat capacity of steel and copper and then substitute in the final. Let's see. So this kind of a question, read well first of all, right? And then let's try to put it into a figure, right? So let's try to put it into a figure. In that case, it will be easy, I guess, right? So this is the 15th question, right? Right. So fine. The 15th question here, initially they are saying, right? Initially they are saying that there's water which is at 24 degrees Celsius, right? So that's water which is at 24 degree Celsius, right? So for this, they are going to put a copper sphere, right? They are going to put a copper sphere which is at 72 degrees Celsius, right? 72 degrees Celsius is going to be put in. So finally, what happens? Finally, what happens is both this copper sphere and the mass of water is going to reach what? An equilibrium temperature of 48 degrees Celsius, right? Both these guys are going to reach an equilibrium temperature of 48 degree Celsius. right? So in that case, let's record it 48 degrees Celsius. Now the heat given by the sphere is equal to the heat absorbed by the water, right? So that's how we are going to do this question, because the container is well lagged, right? The container is well lagged. There's no heat going out of the container. All right. So yeah, there's no heat loss simply, right? Heat given by the sphere is equal to heat absorbed by the water. Heat given by the sphere. Let us assume the mass of the sphere is. Let's assume the mass of the sphere is m, right? Ms. Mass of the sphere is ms, and the specific heat capacity of the sphere is Cs. So let us, since it's a copper sphere, let us give a symbol as simply, let's say the mass of the sphere is mcu, and specific heat capacity of the sphere is ccu. So its temperature varied from 72 to 48. The mass of water, let's assume mw. The specific heat capacity is cw, right? Cw. Its temperature increased from 48 to 24. This is the first equation. So in the second instance, what do they say? In the second instance, what do they say? They're saying uh, when they consider the same, like they are allowing the saying they're allowing the this thing, what you call, the water, the content, to come to reach the room temperature. They are allowing the content to reach the room temperature, which means this is once again in the room temperature, right? So yeah, so when it reaches the room temperature, what they're doing is, once it reaches the cools down to the room temperature theta r, right? So now they are once again inserting. So like after removing the copper sphere, they are inserting what? They are inserting once again another steel sphere, right? They're inserting another steel sphere, right? So they have given the room temperature initially, that is 24 degrees Celsius. If you read it, you will see it's 24 degree Celsius, right? Read the question well. They have given the room temperature as 24 degrees Celsius, right? So in that case, that's going to be easy, right? So right, just fine. So afterwards, what happens is they are going to insert a steel sphere, right? Which was at 84 degree Celsius. So after the steel sphere and water comes to equilibrium, its temperature was new. The new temperature was seen to be as 54 degrees Celsius. So now for the second case, what is it? The heat given by the steel sphere, the heat given by the steel sphere is equal to the heat absorbed by the water, right? So heat given by the steel sphere is, let's assume the mass of the steel sphere is ms, and the specific heat capacity of the steel sphere is Cs. Its temperature varied from 84 to 54. So 84 minus 54 is equal to what? The mass of the water did not vary, right? It was the same old mw, right? The mass of this is mw, cw. It was initially the second process also started from the room temperature, right? So they allowed the first instance to come to room temperature, and then from room temperature only they started the second experiment. So yes, in that case the temperature difference is 54 minus 24. This is the second experiment, right? Okay, finally what does happen in the third process? What's going to happen in the third process? Right. So let us move on. All right. Uh, let's draw the figure for that. So there was a once again after taking out the uh, copper sphere, they allow it to come to room temperature. Actually, the room temperature was initially given to be as 25 degrees Celsius, right? So then thereafter, what they do is they insert both uh, a, a copper ball which is at 72 degrees Celsius and a steel ball which is at 84 degrees Celsius, right? So what happens next is finally they are going to come to a certain equilibrium temperature, right? The copper and the steel, they're going to come to an equilibrium temperature. Let's assume this theta m. And we do not know this theta m, and we need to find this is the question, right? So yeah, let us do the calculation. Actually, you know, the heat in this case, of course, the heat given by the copper ball and the heat given by the steel ball is going to be equal to the heat absorbed by the water column, right? So heat given by the copper ball is mass of copper is MCU, the specific heat capacity of copper is CCU, right? And the temperature difference is what? From 72, it's going to decrease its temperature to theta m, 72 minus theta m. And if you consider the heat given by the steel, it's going to be ms cs. Its temperature decreased from 84 to theta m, 84 to theta m. So this is the heat given by the copper sphere and the steel sphere. So this heat given is going to be absorbed by the water, right? So heat absorbed by water is going to be written how? M W C W. What heat absorbed is, initially it was at 24 degrees Celsius, that the water, and it reached to theta m. So its temperature difference is theta m minus 24. This is the third equation. This is the third equation, right? So what we could do is so here to find this, we need to find what exactly? The theta m, right? The theta m. We can substitute MCU, MCU, CCU from this equation. From the first equation, we can substitute MCU, CCU. If we subject MCU, CCU from the first equation, if we see MCU, CCU is equal to MW, CW 48 minus 24 over 72 minus 48, right? This is the equation for MCU, CCU. Similarly, we can get an expression for MS, CS, that is MW, CW 54 minus 24 over MW, CW, right? So yes, sorry, it's going to be MW, here it's going to be exactly not MW, CW, it's going to be 84 minus 54, right? Right, this equation, what you need to do is this equation and this equation you are going to substitute instead of this part and this part. So MWCW cancels out, MWCW cancels out, and you are going to easily get, if you simplify, you're going to get the theta m to be as 60 degrees, right? So although this seems to be as a very complex question, like a lot of data was given, it's quite easy, right? So what you have to do is from the first equation, you have to subject MCU, CCU, that is the mass of the copper and specific heat capacity of copper, the equation for that you need to subject it. In the second process, you need to subject this thing, that is the mass of steel and mass of specific heat capacity of steel. So both, if you substitute in this and in this point, you are going to get like MWCW is going to get cancelled out in all these cases, and you are going to get T time to be as 60 degrees, right? So I guess that is quite clear, right? So actually, guys, the rest of the questions, the 16th, 17th, 18th, 19th, and the rest of the questions are going to be based on latent heat of fusion, latent heat of vaporization, and all. So I will stop from that point onwards, and we will discuss the latent heat of fusion and latent heat of vaporization part in a separate tutorial session. That is the tutorial session 2, right? So yes, thank you, guys. See you on another session in, right? So, okay.
Oh, yes.